the next thing we're going to, in this algorithm, I changed these equations that account for the gamma inverse gamma situation, but I left this linear regression here. Let's see what that's doing. So if I analyze the kinetic energy directly, so that's kind of the observed variable, I get this rather small, I go from a mean square of 1,656 to a mean square of 210, but I'm also analyzing U and V. So, you know, I can take my analysis of U and V and then go half analyze U squared plus half analyze V squared, and then look at the error of that, and that's horrible. That's got a mean square error of 1,360. So this is similar to what Leonhard Scheck was finding with his assimilation of severe reflectance observations with the LETKF. It looks pretty good in ob space, but it's horrible in model space. There's a big inconsistency there. So we need to replace this by something better than linear regression. So in this serial framework, I'm going to borrow ideas from Fordyvar. So there is, for any observation, Hj, that's the nonlinear operator associated with the jth observation. There are a minimal list of variables required to predict the observation. So in this case, it's kinetic energy. The minimal list is just the U and V value at the site where the observation was taken. So there's just two variables, U and V. For Leonhard Scheck's example, there's a whole vertical profile of cloud water, cloud ice, I think humidity as well. So there'd be more. There might be like 100 variables in that minimal list. Yeah, so what we do is, the first step is we find our best estimate of it. Well, we use the GIGG-EnKF to estimate that minimal list using linear regression. And then we apply the nonlinear operator to that, you know, first guess of what these values should be, this minimal less that we got from linear regression. And we compare that with the analyzed values. So in this case, that'd be the analyzed kinetic energy values. And we'll find that these will be inconsistent. So Leonhard Scheck was showing us that difference from the LETKF. And I just showed you that difference as well. So it's different, and it shouldn't be. We want them to be the same. What we believe, what's good, is this analysis in observation space. I just showed you we made this massive reduction in kinetic energy in, you know, from observing kinetic energy obs. So in this sort of observed variable, we're really doing well. But when we do the regression back to the model space variables, it's horrible. So we're going to hold these analyzed values fixed and do steepest descent minimization of this cost function. I'm going to do ensemble space constrained Newton iteration. So I'll only allow myself to move in the direction of ensemble perturbations, which we hope are sort of physically based. But I'm going to move down those directions until I've got an xi. When I apply the nonlinear operator to that, I'll exactly map on to the corresponding analyzed point in observation space. This is sort of examples like the one I opened the talk with, where you were analyzing U squared. So this would be a univariate case. And I'm just showing you, so this is, say this one here, this is a bit like what I opened the talk with. There's the prior U distribution. We observe U squared. So the posterior should be multimodal. If I do GIGG filter without doing this outer loop, the posterior density I get is this mauve line. So it goes up there, it knows nothing about the bimodality. But if all I do is just apply that tiny little outer loop, it involves like, you know, 3 variables, so it's super fast, the gradient is trivial. Just do that for every particle, I get this cyan line, and lo and behold, I've got a multimodal posterior. No need for a Gaussian mixture model, just enforce consistency between model space and ob space, and do a good job in ob space. So begin by doing a good job in ob space, and then enforce consistency. And that gives, so basically, these are all just little variations on the same thing. Got it right in all of them, except this one, where it's sort of underdoing the negative lobe. It's not, you know, it's not exactly solving Bayes' theorem, but it's not bad. Here's an example that I did with Derek Passelt. This is actually out now. It's not in review. It's actually out. And he's got a one-dimensional cloud model, so one vertical column, and we're observing rainfall rate. And This is just showing the different posteriors we get. If we do the GIGG just with linear regression, this is what our posteriors look like for 3 different rain rates up here. So these parameters, we're actually doing parameter estimation here. So this is a slope parameter, and that's a cloud to rain autoconversion parameter on that side. So these are the posterior densities. The true ones we get from an MCMC, and so they look like this. So refer everything up here to these 3 here for the different rain rates. And you can see by doing the out of this model, observation to model space consistency iteration, you know, it starts looking a lot more like this than it did up there. So really looking a lot better. So they're just, even for the 1D case, you can see how much better you're looking. But let's go back. If we've got a multivariate case, once I've analyzed this, so this XAIH, now I've got this minimal list of variables, the U and V associated with a single observation of kinetic energy. So I've got, you know, ones that are perfectly consistent with the observation space there. And now I'm just going to, same sort of thing as what Jeff Anderson does is in his Dart filter. I'll do linear regression away from that to all of the other model space variables. Yeah? So that's pretty much the normal Dart step. And then I also do the same for updating all the other observed variables. And so in terms of updating the observed variables, I'll normally use this, but every now and then this linear regression will actually give me, so I'm updating variables that are observed, but they haven't been assimilated yet. And sometimes the linear regression will give me a negative value for this. So this linear regression here will say, oh, you've got negative kinetic energy. Yeah? And we know that's rubbish. So if that happens, so if this analyzed Ki that I get from linear regression is less than 0, then I'm just going to take the analyzed XY. So this is the U and V that I got at that same location, apply the observation operator to that and get a positive kinetic energy from that. So that's my rule. So linear regression for updating the obs, unless it obviously fails, and then I actually use the X and Y, the U and V I get from that and compute kinetic energy here. So now, if I do that, the same case, now my analyzed kinetic energy is actually better than it was before because I'm doing things that make more sense. And so now it's 150. And now I can go to U and V space and then apply the kinetic energy operator to that. And I get the same mean square error. So I have these things equal to each other now. So, and now, if before, to show that I was getting a better result, I had to do sets of 50, to show that it was a statistically significant result. Now it's always better by a big margin. So these are just 28 trials. It's better in each one. Over those 28 trials, the mean square is reduced by 75%. The chance of getting that 28 independent trials to win by pure chance is 1 in 2.8 times 10 to the 8. So it's a big improvement. Okay, that's right? Yeah. Right. Good. So that sort of deals with bounded variables and nonlinearity. That's one way of dealing with it that seems to work quite well. But I haven't yet dealt with this issue of on-off variables. So we have stacks of these. Rain is like that. If you've ever been in a weather forecasting competition, it's not a bad bet to just say there'll be 0 rain because it happens a lot. And same with cloud. That can be 0 or you can have cloud. But there's ice is like that. You can have 0 ice or you might have ice. So let's have a bit of a think about that and see whether this gamma, inverse gamma type infrastructure can help us deal with that. So in this case where there's, for example, you've got an ensemble forecast, none of them have rain, but rain is observed. I mean, there's things you can do to make ensemble Kalman filters or 4D particle filters kind of deal with it, but I don't know. But the most suggestions I've heard are not that satisfactory. How do you even deal with Bayes' theorem in that case? I don't know. How do you interpret it? So let's see if we can get somewhere by just thinking about this in the context of the gamma inverse gamma filter. So what I'm going to do is I'm going to form a direct delta function, but from a gamma PDF. I'm going to take it as a limit, which delta functions always are. So let's think about this limit. We're going to start with a prior that is a gamma PDF, and in this case, the relative variance of this prior is 0.707, and the mean of this prior is the inverse square root of that relative variance. And if I do that, then the mean of my prior is this value here, about 1.2, and the black dashed line here is my actual prior. And I'm going to assume here that I have a good observation of rain that's 0.5 of some unit of rainfall. Yeah? And this green line, the green dashed line, is showing me the observation likelihood. So to get the posterior, I multiply the green line by the black line, and that gives me the blue line. Yeah, so that's the posterior. That's what these GIGG equations will give you. So now let's make the relative variance a bit bigger. Yeah? Oh, sorry, a bit smaller. Yeah, so the variance at the top sort of remains the same, but I'm making the mean smaller here. So that becomes 1.41. So now the black line looks like this. Now the mean of that prior distribution is smaller. Yeah? I'll make it bigger again. Now it's 11.3. And now the gamma PDF is this thing here. Yeah, so the prior mean's there. The ob is the green line. Look at this. Remember, the ob was the green line. There's the observed value, 0.5. There's the prior mean, about 0.25. And look where the posterior mean is. Posterior mean's bigger than both of them. It's not locked. Even though it's a univariate experiment, the posterior mean does not have to be, and should not be, between the observed value and the prior mean. So that sort of thinking is wrong when you're dealing with these types of variables. Yeah? Let's take it further. Remember, we're just multiplying the green line and the black line together. That's all we have to do. So we take it a bit further. And now, it's kind of actually the posterior mean didn't change very much. Very similar to what it was before. Yeah, because it's like this green line times the black line. Even though the black line looks like it's 0, it's not quite 0. Yeah? And then I can make that 32,768. And now it basically looks like a delta function at 0. But we have a posterior that has rain. Yeah? So this posterior is still the blue thing. I'm multiplying the green curve by the black curve. The black curve is this very small value. It's almost equal to 0, but it's not quite equal to 0. So that's why I get this green curve. So this is a different framework. So what we're saying here is, like, we've all been thinking Gaussian, yeah? So if everything's 0, that means it's 0. Yeah, but this is different. Now we think about different. No, it's rain. It's a gamma variable. So if all the ensemble members come in saying, and there's no rain in them, what we say is, oh, well, it's one of these gamma delta functions, and so, we multiply one of these gamma delta functions by this green line, and we get rain. Yeah? So you don't have this craziness where because you're looking out the window, it's raining, and your DA system is saying there's no rain because, I didn't have any rain in my prior, so it can't possibly be raining. Yeah? So just by looking at the same thing from this different framework. So I think traditionally we've thought of, we've got these ensembles and we fit Gaussians to them. And then that leads you to this, what do you do when none of them have rain but you observe rain? But when you think of it this way, it's like, it works. It sort of fits with what we know is true. Okay, so now we might have a situation where we've got 50 members that are raining and 50 members that are dry, or some variation on that, so we can compute the probability that it's dry. Yeah, so that W0, that's the probability of dry. So that density, that first one, I'd model that as a, one of these gamma delta functions. And so this is a different case. Now I do have some wet members, but I have some dry members as well. And then I have my other 50 members. I can compute a relative variance from those and a mean and fit a gamma PDF to those. And then they'll get the weight 1 minus W0, where W0 is the probability in the ensemble, the frequentist probability that there was 0 rain. So you can fit this into Dart as well. So we get this. One thing that I didn't talk about was this bit. I'm back to the linear case here. we could do a nonlinear case as well. So I just showed you that with this GIGG-Delta infrastructure, then I can have a situation where none of my forecast members have rain, so they'd all be 0, yeah? Suppose I observe rain, so all my forecast members would be 0, but this GIGG is going to give me an analysis distribution that will be a gamma PDF of rainfall rates here. Yeah, so this bit in observation space is fine. Yeah, I'm good. But how am I going to do this regression? Yeah, this is a regression between rainfall and the different ensemble members. I don't have any ensemble members that have rain. So how do I regress away? How do I regress to the other observations? How do I regress to the model space? How do I change that? So I could do there. So now I start fudging. So there's all sorts of things I could do. I could say, okay, in my 6-hour forecast, I didn't have rain at this location, but you know what? My 12-hour forecast, I did. I can grab, all this is going to be used for is regression, yeah? So I can take the 12-hour members that have rain and do the regression with that. Or I could go back, I could have a hybrid covariance model where I have, you know, ensemble perturbations from last year that are relative to this season, and I could find members within that that have rain in them, and then compute the regression from that. So what I'm saying is, well, I've tied down what's happening in observation space. As long as I do something reasonable with these regressions, it's kind of even based on a climatological type regression, it's not that bad. So that's how that bit works. And this is a little example where I had, so this is a couple model that has those green bars of rain. Don't really have time to talk about this very much. So this is without the nonlinear regression step, but you know, I just did a bunch of experiments, and this GIGG-Delta does better than the EnKF for rain or wind or current. So that's sort of the end of that. And then in my remaining 2 minutes, I just wanted to talk a little bit about, well, to have a discussion about how these ideas might be used in other data assimilation schemes. So I hope, working with Jeff Anderson, to get this whole thing into Dart, so it would be available to everyone. We've got the first bit, the linear bit, kind of in there. Not very, it's in there, not really tested that much yet, but well, a few tests we've done and they're okay. We haven't got the non-linear thing in there yet. So if you're doing ensemble adjustment Kalman filters, you're working with Jeff's stuff, then you'll be able to work with this as well soon. But let's suppose that, no, you've invested in, say, something like an observation space volume like the LETKF or a local particle filter or something like that, or a variational scheme, you've got 4D VAR or something like that, then how could you use this? So one thing you could do is you could use this GIGG-EnKF with the ob to model space iteration to assimilate the bounded variables, yeah, the non-Gaussian variable. Oh, here. So suppose it's the LETKF. You've got your observation volume with LETKF. You just take a model grid point. You use observations close to that to update that grid point. You could start with these bounded variables that you know, the GIGG will be a better approximation for them, and just go through those one by one within that volume to update that central grid point. And then once you've done that, once you've got through these bounded variables, you can do the rest. That posterior ensemble can be the prior for the LETKF, and then you could do the LETKF as usual. Similarly, if you've got 4D VAR, you could do a pre-step to the 4D VAR where you take on these variables that you just felt the assumptions of your variational setup were not very good for, and do this GIGG-EnKF, get through those, and then after that, assimilate other things with the other observations using the traditional variational technique. Almost done. To improve nonlinear trajectories in any of these techniques, I mean, particularly, I guess I'm thinking of the LETKF here. VAR with an outer loop already deals quite nicely, as long as you've got an accurate TLM. It already deals quite nicely with nonlinearities. But the LETKF Gia Evertson, made the suggestion at the opening of this conference, just use a 4D smoother form of this. That's a trivial in an ensemble context to turn a filter into a smoother. And then, you could play this game of tripling. This works for relative ob-error variances as well as normal ob-error variances. You just triple the ob-error variance, do it as a smoother, and like assimilate the ob 3 times. But you've inflated the ob-error variance by a factor of 3. And actually on the third iteration of that, I don't know if you noticed there, but typically the posteriors look a lot more Gaussian than the priors. So maybe on the third iteration, you could just sort of switch over to your Gaussian technique. Something like that would work. Anyway, that's just some suggestions of how you could fit these sorts of ideas into something that you have already. I did try quite hard to try and figure out how to do this all at once in a variational technique. I think it's fine if the only thing you want is, well, no, it's not fine. The observation term is no problem. You might have observation errors that are non-Gaussian. You could put that term into the variational technique. But it's less clear about what you do with the actual model space. One of the problems is, so can you make a gamma PDF multivariate? You can. There's something called a Wishart distribution. But the thing about a Wishart distribution, it has uniform relative variance. The relative variance never changes. It's the same over the whole domain. But that tropical cyclone example I just showed you, the relative variance is changing like crazy. It's huge around the edge of the TC. So it's just like, it's hard to find multivariate priors that have this one, global form that you could minimize with 4D var. We have lots of complex things going on in the atmosphere. Nevertheless, I don't know. There's stuff you should play with. So anyway, I'll just conclude with that, which is, I think I've said all of that. And I'll just take questions. Yeah.
Thank you very much.